The new title, I guess, is Matrix Factorizations. Of course, there are lots of ways of factorizing a matrix, and the numerical analysts love these, and that's not what I'm talking about. So let me begin with a little history, which will make it clear where this particular version comes from. Is this visible over there?
A black marker might be better.
Black is better.
There's some black in the wall too, right next.
You mean this?
Yeah, those.
Yeah, I have one here, I think, too. Let's see. Markers are not my native language. So I think the first time this notion appeared in the sense that I'm talking about is in the work of Dirac back in the 20s and 30s. And he was interested in the Lorentz operator, minus 1 over c squared. That really is the speed of light, d by dt squared, plus d by dx squared, plus d by dy squared, plus d by dz squared. And he wanted, for some reason, a square root of that. Now, that's silly, right? There is no square root. You can't take the square root of a quadratic form of rank 4. But he had a very bright idea for getting around that problem. Let's forget that this is t and x and y and differentials, and think of it as an algebraic problem. And I want to think of it, in fact, in terms of quadratic forms, and I'll work over an algebraically closed field. And so I'll rewrite this as in different coordinates, x, y, minus uv, replacing all the differentials. And he took a square root in the following way. He said, well, if you think of this, this is the determinant of something, and the determinant is the matrix times its adjoint. So if you write a matrix like this, x, y, and uv, and put the same thing, sorry, the adjoint of that down here, which I guess is x, y, and have I got this one? No, sorry.
yx.
Yx, yes. Oops. Erasing, that's the big
It's
On the board.
on the board.
Oh, on the board, good. Right, y, x, do I need a minus sign
Yeah.
somewhere? Yes. uv, maybe there. And maybe the whole thing is the negative of what it should have been.
It should, you need a negative on the u.
Where do I need it?
You
Here.
think you should usually put on the v and the u? Or one of
Yeah.
those? Yeah, it's
Feedback.
negative 1 to the I plus j, so.
Right,
Negative
x,
with
y
minus j
minus uv, there we
And
are.
minus vx.
Minus,
Negative vx.
Minus
Minus
sign.
V.
Yeah,
there we go.
it's, you know, it's, the signs are an anti-diagonal.
that's right, okay, thank you. And zeros up here, and the square of this is indeed, well, it's not exactly this, right? This is an irreducible polynomial, but it's a matrix with this on the diagonal. So it's, if I call this D for determinant, and it looks like D, D, zeros. So that was good enough for what he wanted to do, and he observed then you could factor, in fact, take the square root of this irreducible polynomial, somewhat unreasonably, as a matrix. So that's the first matrix factorization that I know of in the literature. Well, of course, quantum mechanics was wildly successful, but nobody paid much attention to this little corner of it. I got into the game and became interested in this, not knowing about Dirac, actually, around 1979, 1980, and there's a paper of mine in 1980. And I'll talk largely about the results in that paper, but updated by work I've done recently with Irena Peyeva and now Frank Schreier. So I've gotten very interested in this subject again for other reasons, which I probably will only hint at later in the talk, and have worked with them. But this paper is called Homological Algebra on a complete intersection. And as I say, describe some of the results there and how they might be relevant to things that I thought of in computer science. Well, first of all, you could ask, is this somehow special? What's so peculiar about this polynomial that allowed us to do that? Maybe we could do it with more polynomials. And you might notice also that I took a square root here, but I actually had something more primitive in mind, or in hand, namely the product of this matrix and this matrix is a 2 by 2 matrix with V's on the diagonal. So you could think of that as a factorization into different factors. And from the factorization into different factors, we got a square root. So I'll define the matrix factorization. I'll abbreviate it MF. Matrix factorization of a polynomial. F is a pair of square matrices Now, I said a polynomial f, and you could do that. We could also do it with power series. We could do it with elements of a regular local ring. There's a homogeneous theory. I'm sort of going to ignore those refinements for the moment. If you want to be more precise than I am, let's think of this as a power series, square matrices. So F, I'm going to be in the power series ring, F in C if you like, or arbitrary field K. C here stands for an arbitrary field in n variables. And it's a pair of square matrices over this ring, which I'll call S, such that, let's say, AB with A times B equals F times the identity of whatever size A and B are. So they're square matrices of the same size, n by n maybe. So that's a matrix factorization. Now, trivially, these things always exist because I could take A to be F times 1 by 1 matrix, and B to be 1, and that wouldn't be very interesting.
So, David, the n doesn't have to be the same, right?
Ah, thank you. No, it has nothing, this m has nothing to do with that n. M, let's say. Thanks, Greg. So I want to impose some condition of non-triviality. And the way to do that turns out to be to insist that A and B have entries inside the maximal ideal of this ring. So no constant terms. Entries without constant term. And every matrix factorization is one of these. This is called minimal for some reason. One of these plus one with an identity matrix and then F. So in some sense, these are the basic building blocks except for the trivial factorization. So there's a nice, unique theory of that kind. So we could ask when this is possible, and it certainly isn't possible all the time. For instance, if to give a non-trivial, in this sense, matrix factorization. For instance, if I took F to be x1, then, well, its order is 1. If I take the product of two things with no constant term, then I get things with square constant term, right? With quadratic constant term quadratic leading term at best. So there aren't always matrix factorizations. And the theorem, easy theorem, which I'm going to prove for you, which I observed back in the 70s, is that there exist non-trivial matrix factorizations for all other power series. Any power series without a linear leading term. So if you take a power series, no constant term either. Power series vanishing to order 2 or more, or in more algebraic geometry language, a singular power series, then there's always a matrix factorization, and often lots of them. non-trivial MFs exist for any F in the maximal ideal squared. Let's name that M squared. Here capital M is x1 up to x little m. Any singular power series. So we've seen one already. If you take the determinant of this, then we have a matrix factorization. Determinant times the identity. This is the one we all learned practically in high school. Determinant times the identity is the matrix times its adjoint. Right? So that's an example, and one from which many other examples can be built. So how would one understand this? Let me prove this for you. And the proof will give you an idea also that there might be lots of these things, in fact, different sizes. So let's take a module over this power series ring, finally generated module. A module annihilated, however, by F. So let me think of it as over R, I'll call it R, which is S modulo the ideal generated by F. By the way, people should feel free to interrupt me. In fact, if I say something that you don't completely understand, probably some of your neighbors don't either, and they'll consider you a hero and a great help if you're the one who sticks out and interrupts. So don't hesitate. So I'm going to work over this ring R, which is S mod F. Now, I think probably all or most of you know the famous theorem of Hilbert that says that if F had a linear constant, a linear leading form, so if I'm thinking of F always as in M, but if it wasn't in M squared, if it had a linear leading term, then this ring would be what's called a regular local ring, and every free resolution over this ring would be finite. The fact that F is in M squared means that for many modules, for example, for the residue class field in particular, the minimal free resolution of this object M will not be finite. So I'm going to look at the minimal free resolution as a way of exploiting this hypothesis.
Excuse me, I have one question.
Please.
We have already seen that determinantal complexity is well defined, so every polynomial can be written as a determinant.
Ah, very good.
Does it already settle this for polynomials? Like, because you said the determinant has a matrix.
Absolutely true. So that's a good point, and in this audience I can say you all know that things have matrix
okay.
factorizations. Of course, that doesn't, yeah, I guess even you can get non-trivial ones that way. I'm going to produce lots more for you.
Okay.
But I think but here the issue is homogeneous, right? So you want the polynomial as a determinant with linear homogeneous entries.
Yes.
That's even better.
But
Wait,
that's
linear hasn't shown up here.
Okay.
Yes,
Oh,
power
Okay,
series
and
effect.
but we want the entries to be in the maximal ideal.
Right.
What Jesko has in mind, there will always be constants in the matrix.
Right.
That's disallowed.
Yeah, I get what you're saying.
Uh-huh.
Okay.
Ah. But you see, I could always write it as a sum of the ones with constants and the ones without, so it's not far, but you need to know a little more maybe than just that statement. Okay, anyway, let's take this module and make a resolution. So what that means is I want to compare the module to free modules. So for a start, I map a free module onto it. In other words, I choose a set of generators. I could choose a minimal set of generators if I like, and that will make my life simpler later, so let me do that. So there's a minimal set of generators encoded in an epimorphism from a free module onto my module M. Well, there's my first comparison, but maybe, and this is Hilbert's idea, old idea, but maybe M wasn't free, and then this isn't a very good comparison, because these are quite different. And Hilbert had the idea that, well, let's throw in the generators of the kernel into the description. And I can encode that and compare them to a free module by mapping a free module onto that and one. And I can continue, potentially forever.
So if I think of R as the coordinate ring of the zero set of F.
Yes.
And then M is will M always be the coordinate ring of the subvariety of that
No.
vector surface?
You can certainly
Or
take it
general?
M to be that, but it's in general a sheaf on that variety, if you like, or it's interesting to take vector bundles of various kinds. I guess not vector bundles in this setting. In the homogeneous case, you could ask for vector bundle on the projective variety, which would be, in this setting, a module which is locally free off the maximal ideal. There are lots of modules you can take, but if you don't have your favorite module in mind yet, then think of M as the residue field of S, of R. Okay? That's sort of the basic module from this point of view, or a basic module. So I could certainly take M
But
to
by
be
residue field, you mean R
S
mod the
mod M,
maximal ideal.
or R mod M, right.
Right.
But if my favorite module is the ideal or coordinate ring of the subvariety, I won't.
You're
run into
perfectly
trouble.
welcome to take, this is, by the way, the coordinate ring of a point, right?
Okay.
So this is even more special than that. Anyway, whatever the module was, we can begin this process, and we can continue this process, and we can keep continuing this process, and we'll probably never stop, right? Because Hilbert says that you stop for every module if and only if, or Hilbert and Buxbaum and Sayre, Auslander, Buxbaum, and Sayre, say that you stop if and only for every module, and in particular for the residue field, if and only if f has non-zero linear term, assuming f is not a unit to begin with, in which case this would be 0. Not so interesting. Okay, so since I assumed f was in m squared, many modules will have a resolution that continues forever, and that's good from my point of view.
Wait, then you want to do the resolution over R instead? You're doing it over S right now.
R, thank you. Yes, I said it and I didn't do it. Didn't write it. These should be R's. I'm glad you're more awake than I am. Good. Yes, very important. Over S, of course, it would have a minimal resolution, and I'll use that in a moment. So after a while, in fact, after m or m minus 1 steps, we come to a module that is in some ways better than m, and I'll try to describe that. So let's see. This module is the first, so I really want the mth, or even m minus first module, so I guess the interesting place for me is fm, which is r to the n's of m maybe, and then there's a module here which I'll call m prime, which is the image actually. Write it better. Fm minus 1, dot dot in the middle, and this module here, which is the kernel, I'll call m prime. Now, I claim that in a very precise sense, the kernels get better as you go back in this resolution. In the case of that Hilbert worked with, or Auslander, Buxbaum, Sayre worked with, when f has a linear term, non-zero linear term, the modules would get so much better that they become free after a while. But here something similar is happening, and it's important to understand what. So what I'm about to say is usually done by introducing the notion of depth and discussing the Auslander, Buxbaum, Sayre theorem. But I'm going to cut to the chase and just tell you what the important point is, that namely the projective dimension of m prime as an S module now. So m prime is an R module. I certainly can regard it though as an S module because R is a quotient of S. And the projective dimension of m prime as an S module is 1. In fact, the projective dimension went down steadily as I went back in this resolution, if it wasn't 1 before. Here, I don't know, I took an arbitrary module that has some projective dimension over S. If I took the residue field, it would have projective dimension little m over S. And the theorem that one proves, and this is basic commutative
So
algebra.
what's projective dimension?
Sorry?
What's projective
Oh,
dimension?
sorry. It's the length of a minimal free resolution. Right?
Okay.
So i.e., I can write 0 to G1 to G0 n prime to 0, where G1 and G0 are free over S.
Do you want to have most one?
Sorry?
At most one?
At most one, yes. That's the same statement, however. So it might have had finite projective dimension as an OR module, in which case this process would come to an end here, and m would be 0, and not so interesting as other cases. But if it had infinite projective dimension, for example, if it was the residue field, then I couldn't do any better than this in comparison to the free margin. And in fact, what happens is that the projective dimension, if the projective dimension of n is more than 1 to begin with, then the projective dimension of the first kernel is 1 less, and it keeps going down until it gets to 1, and then it stays fixed at 1. That's what Austin-Brooks-Combe-Serre tells us. So this is a relatively big theorem, but I'm going to assume it. That's a theorem that stands at the beginning of homological algebra and commutative algebra reading. Okay, so what? Well, these modules, in particular m prime, are all annihilated by f. So let's use that. That says that anything in f times g naught will go to 0 there. That means it came from something in G1. So I just choose a basis and do it for each element of a basis. And that gives me a map going back from G0 to G1. I'll call it sigma. I'll call this map D. And what I just said is that if I first do sigma and then do D, I get F times the identity. A familiar expression. Now, life is even a little better than that.
Sorry, what's sigma?
So if you like, sigma is defined by this equation. But anything times f times g naught goes to 0 in m. So f times g naught is in the image of d. Right? And therefore, if I choose a basis of G naught, so E in G naught, there exists E prime in G1, so that D E prime is E. And if I do that for every element of a basis, then I've constructed a map sigma from G naught to G1. So I'll define E prime to be sigma of E. That's not a unique choice, of course, but it's, well, maybe it is a unique choice, actually, because this was a monomorphism. So there's only one E that goes to a given element. Okay, so that's good, but more is true, actually, because sigma D is also equal to F times the identity. As well. And you can see that because to say that d sigma is f times the identity, well, just think of f for a moment as an element of the quotient field. That says that sigma is the inverse of d times f. And inverses are two-sided, right? So I can write it in the other order too. So the fact that f is non-zero and a non-zero divisor is what I just used. And it says that d sigma equals sigma d equals f, and that's a matrix factorization. Okay, so I produced for you from any module of infinite homological dimension, not a finite homological dimension, a matrix factorization. A minimal one too, because, well, that takes a little more argument. Why is it minimal? First of all the maps that I chose had entries in the maximal ideal. That's because if one of them failed to, then I could cancel a generator in the next term. This wouldn't have been a minimal choice of generators at each stage. And here, if I didn't have minimality here, then it turns out I would get an element, a basis element of G naught, which was F times another basis element, and or sorry, an element of G1 mapped to F times another basis element, and then M prime would have a free summand, and that's excluded by this minimality process too.
At some point one should say, wait, rank of G1 and G0 is the same.
That's, yes. So, of course, that follows from what I've just said, right? But it's true because if I tensor this whole thing with the fraction field of the power series ring, the Laurent series, then M, of course, becomes 0 because it was annihilated by F. So this becomes an isomorphism, and that shows that I have two vector spaces of the same rank in order for there to be an isomorphism between them. Right. So, yeah, it's another useful remark. So there's remark 1, and here's remark 2. Rank of G naught equals rank of G1. All right, so there's a matrix factorization. Now, you could ask what that could possibly have to do with this resolution. And the story is nice here, because in fact that matrix factorization determines the rest of the resolution. You don't need to know anything more, you don't need to make any computations, you can just write down the rest of the resolution based on this. And that's what I want to do next. So matrix factorization is not accidental that they come from resolution. It's sort of built into them.
So if we were to want to put this on a computer, we could just, is there a straightforward algorithm, I mean, like to construct G0, G0 just from Macaulay 2, for
Yes,
instance?
Macaulay 2 will do this in a flash for you. And much more, I'll tell you a little more what can be done in programmed unit. Yeah.
So if we take F to be the determinant,
Yes,
and
for
we want to
example.
recover our favorite one that we started with, what should we take M to be?
Well, it's not uniquely determined.
Right, so what is an example of an M that would give us back
The
our
easiest
original starting
example
point?
is that I take F1 to F0 to be the original matrix. And then it's already of projective dimension 1 over
Which-
S, and the kernel is there.
So what's M then?
M is the co-kernel. So if I'm looking at det X,
Oh, sure.
if I want to factorize det X, I can take M to be the co-kernel of X.
Sure.
And then I don't have to wait M steps, I get my answer immediately. in fact.
Because you're actually in that situation.
And I'm in this situation, right? D is X. I guess I should write X
But
bar
wait,
here.
X is a
X reduced.
matrix with variable entry.
Yeah.
Yes, so I could
Yeah.
take det X, when that's, sorry, co-ker X, which happens to be equal to the co-kernel of X bar, where I regard X as a matrix over the ring R. And this is true, this is the right exactness of tensor product, basically.
I see.
Because this one I get by tensoring this with R over S.
Then D will be the cofactor matrix.
And sigma would be the cofactor
Sigma,
matrix, right? Right. Right. Unique choice for sigma.
Well, yeah, we know what it has to be. Just right.
We could ask, are there other
There.
matrix factorizations, right?
Mhm.
That's a good question, and the answer is yes, and we'll see a little bit of that in a moment. In fact, there are a lot of other matrix factorizations, and that might be a useful fact to know for the question of the permanent. All right, so I want to continue this way a little bit further and tell you how to build free resolutions from matrix factorizations. We went in one direction, we built a matrix factorization from a free resolution. I want to go the other way. So, proposition, a theorem, that's this. Be generous and call it a theorem. If AB equals F times the identity, is matrix factorization over S, then the complex, let's see, so let me write A is a map from, let's say, F1 to F0, and B is a map from F0 to F1. And so when I say AB equals F, I mean the map that I get by going from F0 to F1 and coming back, right? And I could write it the other order too. So if I look modulo F, if I set F equals 0, then AB becomes 0, right? So it's a complex if I write A's and B's next to each other. So here's the complex, F0 bar, this means tensor, F0 tensor R, and then F1 bar, and here's A bar, did I get this right? Yes. And then I can do F0 bar again, here's B bar. So now the composition of these is 0. This is F1 tensor R. Anyone who's confused, not familiar with this, this is just the same basis, right, used to make a free module over R. And I continue peacefully in this way. I get a long complex. And the theorem is that this is a free resolution. In other words, the homology of this has no homology except at F0. In every place, the kernel is equal to the image. In other words, the kernel of A bar is B bar, the image of B bar, and by the symmetry of this thing, the image of B bar into A bar. Sorry, the kernel of B bar is the image of A bar. So, quick way of saying it, this is exact. Or acyclic would be a better term than homology here. Okay.
And I should have asked this earlier.
Yep. Not too
But
late.
is there
Never
an
too
easy way to read off the, I don't know what they call it, rank or dimension of G0 from your starting point of M?
Ah, a very good question indeed. The answer is no. I don't know such a way, except by computing. However, there are lots of conjectures about what the rank can be, and I'll come to that after a bit. And the interesting point, let me try to excite some interest in here, is saying that the good part of the conjectures is that very often, in a way that I'll try to make more precise, we believe that the ranks of these matrices, and indeed the size, will be exponential in some natural measure of the complexity of F.
That's what we want.
That's what we want, right. So that's what should be true. That's been conjectured rather a long time in my field too. So I'm not sure that I'm going to add to a proof, but nevertheless, it's an interesting connection. Okay, so let me prove this for you. This is an easy one. It doesn't even require anything about free resolutions. This is just formal. So here I have, what does it mean to say this is exact? The fancy way of saying such a thing is that if I have a free module mapping to F1 and composing to 0 with A, then it factors through B. The map factors through B. So let me write that sort of schematically. Here. So here's A bar, and here's B bar. And suppose I have some other map, let's call it C bar, which composes with A to be 0. Right? That's the picture I have to think about. These are all maps of free modules. Then I have to find a map here, call it phi or something, that makes the diagram commute. That's what I want to prove.
I don't understand what you wrote there.
It's a little unclear because the bar looks like a tor. Let me see if I can clarify the notation. So I have, what does it mean to say that a map map B bar covers the kernel of A bar? It means that any time I have a map that composes with A bar to be 0, it factors through B bar, a map from a free module, right? well, I could take an element if you like, a rank 1 free module. That's a more primitive way of saying it. Okay, is that clear? This is the time to ask. Or at least it's a time to ask. Okay, so I'm going to prove that. So what do I have? I have C bar, A bar, composed the other way, of course, so A bar following C bar is 0. That's
So-
what I've got.
So you have some F 2J, then F2J plus 1, then F2J plus 2 bars on the top. I mean, you kind of left those out, right?
Yeah.
There's a,
Yeah, that's right.
so you have F2J.
And because of the
F2J
symmetry of
plus
A and
1,
B, it'll be the same if I go with B
F2J
first
plus
and
2
then A.
bar. And then this thing is this phi is going down to what you were calling M prime before, but we don't know it's.
No, M prime.
Prime is on the right.
What is phi?
What?
Phi is going down to
I have
something.
to
in the-
No,
produce
it's going
an
up,
F
actually.
phi.
the
Oh,
math
phi is
goes up.
going up.
Yeah,
Right, 'cause
sorry.
That's why I was
I
confused.
drew it going with dots. I drew it upward, but nobody could see that.
But all
So,
the arrows are pointing.
an
all the other
arrow
arrows
would be a good idea, yes.
There we go.
So I want to prove that there exists a phi making this triangle commute.
Yes.
Right? So and what I'm given is that A bar and C bar is 0. Okay? So, okay, what does that mean? If A bar, C bar is 0, this is, remember, over R. This is working mod F. So just lift them to matrices over S, any old way. Just pick your favorite elements over S that fill in those matrices. I'm thinking of everybody's matrices.
And why do we have, I mean, we have C bar, A bar equals 0. Why is A bar, C bar equal to 0?
Oh, I don't,
You compose.
this C bar is going first. C bar and then
Oh.
A bar. I'm
Okay,
always
good,
confused
good.
by that. too.
Yeah, I'm good now.
And if I'm...
That's why
if
all
I'm
the
not-
algebraists wrote the arrows in the other direction and compasses
would-
the other way.
Yes, well, people have tried to change that. Yeah, so what can I do? I can lift all three matrices to S and see what happens. Right? So in particular, the equation, well, I have a given lifting of A and B, namely the matrix factorization. So I'll think of that lifting of A and B. I lift C bar any old way. And what I get is that AC is F times something, right? That's what it means to be 0 after I reduce mod F. F times D, maybe. Well, it's sort of annoying that I have an F on this side and not an F on that side. But I can fix that by multiplying everything by B on the left. So this certainly implies that BAC equals BFD, but F is a scalar, right? So it commutes with everything. FBD, sorry, FDB. Yeah, BD, right? And now BA, that's a matrix factorization. AB and BA are both F times the identity. So this is F times C is F times BD. So I cancel the F's, right? So C equals BD.
That's what you needed.
And that's what I wanted. This is D bar. Bingo. I said phi equal to D bar. Okay, so that was easy. So there are exact sequences that come from matrix factorizations, and matrix factorizations come from resolutions. Very nice symmetrical relationship.
So I guess this also says that that's eventually periodic, period 2.
In particular, we've just proved that every minimal free resolution over a ring like this is periodic, a period at most 2. Right. It could be period 1
Sure.
also, right?
Sure.
Yeah. In the non-commutative case, you can have periodic resolutions with over nice rings, group algebras, things like that, with longer periods. You can't have, for any complete intersection, any periodic resolution will be period of most 2. But there are funny rings over which you have long periods, 2 commutative rings. This is more or less the thesis of Irina Peeva and Vesko Gasharov under Avramov. Okay, so let's go on with this. Now, so we have some matrix factorizations. As I say, the matrix factorization isn't completely unique. You might start with many different modules to get the same thing. So one immediate question you could ask is, are there really a lot of them? Well, of course, if you have two matrix factorizations, you could take the direct sum. So there's a kind of cheesy way of making more. And there is a Kroll-Schmidt theorem, that is to say, every matrix factorization is the direct sum in a unique way of indecomposable matrix factorizations. So the right question was, are there a lot of indecomposable matrix factorizations? That's the first question you might ask about this. And the answer is sometimes yes and sometimes no. But it's quite an amusing answer, because it corresponds to an answer which is extremely well known in other contexts. So let me write it down for you. This is a theorem of Buchweit, Scroyle, and Schreier. Schreier. The same Schreier who's sitting in the audience there. And it says that there exists only, so given f, and I'm now going to work over an algebraically closed field of characteristic 0, so much is known in other cases. So if C is algebraically closed and characteristic 0, then f has only finitely many indecomposable MFs if and only if f is an ADE singularity, which means either f is of the form x to the k plus 1 plus squares, y squared plus, I'm renaming the variables, of course. This is the AK type, or dk, which is x squared y plus y to the k minus 1 plus squares, or E6, E7, or E8, and that's the end of the list. For instance, E8 is x cubed plus y fifth plus squares. These are the well-known things: x cubed plus y fourth plus squares, and x cubed plus xy cubed plus squares. So those are the whole list. There are 2 infinite families and 3 exceptional cases, and that's the end of the story for finite matrix factorization. So you can see from this that matrix factorization somehow linked to things that, other things that people think about. These are connected with Lie groups, they're connected with all kinds of other phenomena.
Well, that means that the priority of f has an AD singularity?
That's right, yeah. Locally at the origin,
Exactly.
AD singularity.
And otherwise it's
And otherwise it's infinite. And the ones with countably many have also been classified, amazingly enough, and there aren't very many more.
Extended diagram.
Sorry? And there's a, yeah, that's right. This is work of, I didn't write down the author. You know, Frank, it's Wiegand and, is it Buchweit and Wiegand? Anyway, Wiegand was involved, I forget. Avramov and Wiegand.
Can you just say again what goes in ... for these?
Squares. New
all
variables
cases.
and squares.
But
So
the
you can stabilize any
More
equation
variables.
by adding more variables.
More
and
variables.
Squares and more
E6
variables.
one might need adjustment.
This is all up to
Okay.
analytic change of
Up to
coordinates.
analytic
Yeah.
change of coordinates, absolutely right, yes. Or up to formula. I'm working in formal power.
So these have to do with what exceptional fibers you get in a resolution.
You can resolve, there are
Yeah.
infinitely many different
I
descriptions
understand,
of these
but
five
is the countable one also expressed that way in terms of the geometry of the smoothing?
Yes, so you can recover the matrix factor. The matrix factorizations correspond to components of the of the resolution, if I remember right. Frank knows more about
In the
this.
surface case, it corresponds.
In the surface
Sure,
case,
sure.
right. If you stabilize so that it's three variables,
Yes.
then the matrix factorizations correspond to the components of the resolution graph for the minimal resolution.
Okay.
But there's also this in the algebra description. There's a lot of stuff. Cynthia.
So if you fix the size, do you still get infinity? If
Say-
you fix the size of the A and B?
Yes, you do, and I will. So maybe I should tell you something amusing along that line. For example, let's take the determinant. And let's look at matrix factorizations for which, and I'll explain the connection in a moment if I have time, but matrix factorizations for which the determinant of A, so the determinant of A, I didn't say this yet, but maybe it's time now. If I had this equation, then the determinant of A times the determinant of B is a power of F. And if F was irreducible, which is certainly the most interesting case, like the determinant, then that means A and B have determinants equal to a power of F. Which power? So let's say the power is 2. Let's say the determinant of A is the determinant squared. Okay, we have a matrix factorization where F is the determinant. Then Buchweitz and Luschke, I didn't want to say, proved that there is no finite dimensional family that includes all matrix factorizations of that type. So there are families of arbitrary size, arbitrary finite size, with matrix factorizations of the determinant, size, actually I think it has to be even size determinant, and bigger than 2, where the determinant of the matrix in the factorization is the square of the ordinary determinant. That's a pretty strong result about non-finiteness of these things. And the square, the power of the determinant that appears is really the rank of this module M prime. So it's a natural invariant from that point of view. I have the paper here, you can read it yourself. Frank is skeptical about this result, but I think I quoted it correctly. We can settle this afterwards. Okay, so that's something to say. Why the squares here? There's a beautiful theorem of Horst Knurr, which is a periodicity theorem. If you take any power series and add a square, you can ask what happens to the matrix factorizations. And what he proves is that if you add 2 squares, then you get matrix factorizations that exactly correspond to the old ones, but are twice the size. And if you add 1 square, you get either the same number or twice as many. There's a simple way of describing it. So, but adding 2 squares is sort of the simple thing to do. And I could prove that, but I think I have other ideas in mind of what to do next.
So David,
Yeah.
I should have told you before, the Simons Institute has requested that any talk over an hour, such as yours, have a short break in the middle.
Wonderful. I'm glad
And,
to.
and
Is this a good time?
this would be about the correct time.
Okay, fine.
Just like 2-3 minutes.
Okay, everybody gets up and stretches and goes to the bathroom.
That's right.
Things like that. All right, so any questions about where we've been? We saw that if you take a power series with no constant term and no linear term, so a singular hypersurface is another way to say that, then there are always non-trivial matrix factorizations, indecomposable, non-trivial matrix factorizations. Generally speaking, there are quite a lot of them. This is an extremely special case. And they correspond in some funny way to these periodic resolutions. That's sort of where I am in this talk. Right, any questions about any of those remarks or how we got there? Do you want to see any of that again? That's a legal question. I always feel in concerts of new music, modern music, by which I mean music I didn't know before, that I really wish they'd play it twice, because I like it so much better the second time. So I'm perfectly willing to repeat
Is that
it.
John Cage piece?
Well, maybe not that. Sorry.
Did I understand correctly that if we fix the determinant of A to be f squared, and if we are not in one of these cases, still we can find infinitely many?
It depends on the case, and I don't know that for every thing. For example, in fact, it's not true. For instance, if you take a quadric of the sum of n squares, 2n squares, then the smallest matrix factorizations, or in that case, we know exactly the matrix factorizations, even over a non-algebraic closed field. Frank and I worked on that one time very happily. And the smallest matrix factorizations there are only two of them, and they both have linear matrices in them, and the size of the matrices is 2 to the n. And the determinant, therefore, is 2 to the n minus 1 power of the quadrant. So there may be no low-degree matrix factorizations in that sense.
But when f is the determinant, this is the case?
If f is the determinant, then if I read the paper of Buchweitz and Luschke correctly, that is the case, yes. Yeah.
So Cynthia explained to us certificates for positive Stellensatz, or
Yes.
real Stellensatz, as being a polynomial plus sum of squares. And all of your examples here have that form, some polynomial. Is there a nice connection between these polynomials and what they're certifying and some real variety is not empty?
That's a good question. Let me explain the appearance of the sums of squares. I think it comes from a different source, but let me explain.
Well, I think
It's
these
very easy to
squares are
explain.
just variables.
Sorry?
These squares here are just variables.
They're new, distinct
Stabilization.
variables. That's right. So let me explain where those come from, and then you can judge better than I can. Why the squares? So there are two questions. I think the next two questions I want to address is why the squares, and that won't take very long, and then why the periodicity. What is this? What's the periodicity? So why the squares is this theorem of Horst-Knurrer, Knurrer periodicity it's called. And the easiest way to write it down is as a formula. So Knurrer periodicity. This is not the resolution periodicity, it's a different one. If you have f times the identity equals d times h equals h times d, a matrix factorization, then f plus x squared, f plus xy. xy is the same as x squared plus y squared in my world, right? Because it's x plus iy times x minus iy, so I change variables. F plus xy, this is new variables, two new variables, so they could be old ones too, is equal to, times the identity of course, a bigger identity, is equal to x times the identity, y times the identity. For example, I could write here d and minus h, I guess, and then I could write y x minus d h. Okay, so I double the size, and I get a new matrix factorization. And this is a one-to-one correspondence between matrix factorizations of f and matrix factorizations of f plus xy. That's what Knurrer proves. Of f and nf of f plus xy. Right. So adding xy is the same as adding two squares, and that's really where the squares come from in all these formulas. I don't have anything new when I add a bunch of squares, so I just throw them in for free. Right. Takes a little proving to do this. As I said, there's an intermediate step. You add one square, and there's some invariant theory argument, but that's what's true. Now, what about the periodicity? Where do periodic resolutions come from? You might think this is a pretty special way of getting a periodic resolution, after all. Matrix factorization, but it isn't. And the idea is this.
Question.
Yeah,
When you say finitely many factorizations, you mean up to homological?
I mean up to, isomorphism in a natural sense, but yes, there's a homotopy involved. Of course, free resolutions are never unique, right? Unique up to homotopy. But I do want to talk about indecomposable ones and sums of indecomposable ones. So I have to have equivalence under sums, under the homotopy relation, that's right. So there's a category, a natural category of matrix factorizations. Maybe I'll come to that in a moment. This eraser works even better. So, in a certain sense, I'm going to reiterate what I said before, but now what I say will apply actually in a more general case. So maybe I'll say it in a more general case. So suppose so I'm going to start with the same ring S, which was power series of something in a lot of variables, or any regular local ring, and there are more general things too. And then I take R. Now instead of factoring out one polynomial, I'm going to factor out a bunch of polynomials. Let's say C of them. R equals S log F1 of FC. And I'm going to study resolutions there. Now, so that's what I did with C equal 1 before. There's a special feature of C equals 1, however. Any one polynomial which isn't 0 is a regular sequence in this ring. And I need regular sequence here to make things easy. So if I just take an arbitrary ideal generated by C functions, then free resolutions are just awful. And even the free resolution of the residue class field is not well understood. So I don't want to do that. I want to take an easy case. I had an easy case before. It would be nice to have a little bigger easy case. And the right one is a complete intersection. There's a real watershed after you need that case. And that just means that the codimension of the variety defined by the vanishing of these things is C, the biggest it could possibly be. So let's assume that the codimension of the variety of F1 of C equals C. It's always less or equal to C. The case when it's equal to C is the simplest case. Usually one says just that the F's form a complete intersection or a regular sequence. Same thing. And then you can do the following thing. If you have a resolution over R, so let's say we're over R, and we look at a free resolution, minimal free resolution, then, well, again, F0, F1, F2, and so on. These are the bars, the things with bars, I guess, before. Oh, no, they were unbarred things before, too. So some M. And let's call all the differentials D, not to confuse ourselves with indices. Then D squared, of course, is 0. So if I take these matrices representing D and lift them all back to S, let's lift D to some matrix D tilde over S. Then again, before what I did was to say D tilde squared was something times F, right? Well, now it's something times the sum of F. So D tilde squared can be written as summation Fi times some maps Ti. Let me put tildes over the Ti's for convenience. And then I say that if I define Ti to be Ti tilde tensored with R, in other words, I just reduce everything to mod R, mod F, the F's again, then those T tilde, these T's go this way. And here's a T, and there's a T, and so on. They're operators of degree -2 on this resolution. And the theorem that generalizes this one about hypersurfaces, the case C equals 1, is that these T's eventually become surjective. In the other case, the ranks of the F's were constant eventually, that can be proved separately, and then surjective is the same as isomorphism. But in general, what you have is something like this.
So are there indices on the, you don't need to draw them in, but are there indices on the T's?
There are indices on the T's and on the D's, yes. In fact, there are double indices on the T's.
No.
There are different T's, yeah, I'm sorry, these are each Ti.
Each Ti gives rise to a sequence of those.
Right.
Okay.
Or more generally, what's really true is that I can make one map of the T's, and there's one big map T, maybe I should call it capital T, I don't know, which goes from Fi to Fi minus 2 tensored with R to the C. Now, one way to analyze these and to say something more intelligible about them than what I said before.
So the statement, each of these TIs becomes surjective? Still?
Oh, let me say it better in a minute. That's something like that is
Now,
true.
now things are much bigger over there.
Yes, this is certainly not going to be surjective in general. But I'll tell you what's true in a more precise sense. So one way to test whether a map is really doing something for you is to tensor with the residue field and then see, because then you have a map of vector spaces, you might understand something. And here we have infinitely many vector spaces after we tensor with the residue field. That's sort of annoying. But we could put them together and make a module out of them using the T's. The T's commute, it turns out, mod the residue field. So what's true is that the Ti's make X, that's the same thing, star over R, C, into a finitely generated module over the polynomial ring C of T1 of Tc. That's sort of the general statement here. It's a whole lot weaker than what we know in the case C equals 1, but it does incorporate the periodicity, because if C were 1, then this is the polynomial ring in one variable, and we all know what modules over the polynomial ring in one variable look like, and the only ones with infinitely many sum-ends are the free ones. Right? So this would be, after you truncate it a bit, become a free module, and that's the statement of periodicity, if you think about it. Now, really it's two modules, right? Because there's an odd module and an even module. And one of the old problems about this, except in the case C equals 1 where it's easy, is what is the relationship between those two modules? Nobody understands which pairs of modules can arise, even in C equals 2, although we know more there. So that's an interesting question. Because really, X even of MC and X odd, this is the direct sum, X odd MC. And what they have the same multiplicity, they have the same dimension. There are clearly connections between them, and we don't understand what those are. So that's a problem that has troubled me for many years. Now, back in 1980, I proved this theorem, and it's not terribly hard to prove. I could show you the proof in a little bit of time. But As I say, it doesn't really tell you anything like as much as what you have in the case C equals 1, where you have these nice, very concrete periodic resolutions. What it does do, what these operators TI do, is to allow one to construct non-minimal resolutions. So if you know everything about these lifted T's, or if you understand this process a little more, there's a way of constructing non-minimal resolutions of a module, at least for a module of the right projective dimension. C is the right answer. So if I take an R module which has an S module has projective dimension exactly C, which is what happens for isyzygies, then there's a way of constructing a non-minimal resolution over R from the resolution over S. And that's what we did here, too. We went from the resolution, which is just one step over S, to this periodic resolution over R, but we got a minimal resolution in this case, and in general you don't. And that was a kind of missing point in the theory for a long time, and my interest in the subject recently has been around fixing that point, and Irina Peyeva and I have what we believe is the right answer there. It's a good deal more complicated, and I think I won't go down that path right now. So what I did want to do was to go back to the determinant and permanent. I don't have anything new to say about that, I think, or very little in any case. But Frank and I began talking about it, and it strikes me as a very interesting connection. So I can tell you a little bit about the analogous situation there, the permanent situation. I assume nobody wants to ask questions about complete intersections other than codimension 1. But so let me go back to codimension 1. If you are curious, you can find work by the first paper anyway by Peyeva and me on the archive. So permanent and determinant. Oh, I guess I did want to say something about ranks. Well, maybe I can say something first about the permanent determinant. Permanent versus determinant. So of course we have this nice matrix factorization of determinants, right? Determinant is matrix times adjunct matrix. And the natural question is, what's the smallest matrix factorization of the permanent times the power of a linear form, let us say? Wouldn't that be nice to know? Of course, I don't know the answer. It's not obvious just by looking that there are any, but of course we know there are, because you can express the permanent times power of linear form as a determinant of a bigger matrix. So for instance, for the 3 by 3 permanent, you probably all know this, but I learned it fairly recently, is times power of a linear form, in this case algebra force, is equal to the determinant of a 7 by 7 matrix of linear forms. So that says that that you get at least a 7 by 7 matrix factorization of the permanent just by setting this new linear form equal to 1. So we have an inhomogeneous factorization of the permanent of size 7. And the first power of the permanent is what we get. Now, there are strong restrictions on what you could have that way, which come from this theory a little bit, and I want to indicate them. This is half-baked stuff that I'm about to show you, which Frank and I have been discussing, but didn't get very far with. For example, let's ask, are there 3 by 3 matrix factorizations, or in general, for the permanent, size n permanent, could there be an n by n factorization with linear entries in one of the matrices? Right? Could it be the determinant? Well, you all know that it couldn't. Here's another reason why not, perhaps a reason you didn't know. The hypersurface defined by the permanent, so R equals S mod let's say n by n permanent, n by n generic permanent, has its singularities in quite high codimension. I'm sure you know that. That implies that there are no matrix factorizations of the permanent where the determinant is the permanent itself. No homogeneous matrix factorizations where the determinant is the permanent. And the reason is that that would correspond to the Cohen-Macaulay modulus, let's say, of rank 1, which is an element of the Picard group of the smooth part of the permanent. And Lefschetz theorem says that that Picard group has only rank 1 over the projective space. So Lefschetz says that the Picard group of the perm, and I'll take the non-singular part, the regular part, is just, I'm thinking of this as a projective variety now, is just Z. And that implies that the only rank 1 modules like this that you could get, the only M's that appear as the co-kernel in a matrix factorization, are the free module. And then it's a trivial matrix factorization. And so there are no matrix factorizations where the determinant of the matrix is the permanent itself. So if AB equals perm times the identity, then the determinant of A is divisible at least by twice by the square of the permanent.
So what goes wrong in the 2 by 2 case?
So in the 2 by 2 case, there is of course the matrix factorization, which is det times the other. This only applies when the codimension of the singular locus is at least 4, and in the 2 by 2 case there isn't enough room.
2 by 2 case, the singular locus is empty.
For example, well, true, but
That's
the
a
variety is
dimension.
only 3-dimensional, so the empty set isn't small enough. That's right.
Okay. It depends on the dimension of the empty set is -1 and minus infinity.
Right.
So you're saying this, the theorem about the Picard group is Z needs the codimension of the singular locus
Needs
is 4.
Dimension of the variety.
Needs you to have a dimension of the variety, which is 4, and I guess the codimension of the singular locus has to be at least 4.
Right.
And
But the Picard group is still Z.
Take the hypersurface.
the Picard group is
Okay, there's a quadrant.
So Z plus C.
Z cross Z.
Z cross C, so that's where it fell.
Yeah, right.
So what is the codimension of the single locus of the permanent?
So that's,
It's,
The n by n?
well, so 3 by 3, it seems to be 9. Or-
no.
No.
Sorry, 6. Dimension 3.
Dimension.
Yeah.
But for n by n,
And for
do
n
you
by
know the
n-
dimension?
I guessed that it was bigger than the case. So for the determinant, it's 4. And for the permanent, it looks bigger. That's as far as I got.
I mean, it's generally expected to be N, but I don't think there's a proof.
We don't know.
I see. You don't even know that it's bigger than for the determinant?
That's probably known, but
Yeah. All right, so all I need is bigger than the determinant for this theorem. But I retract and say, as I said, this is half-baked stuff. I'm telling you, maybe only a quarter baked. But I think interesting, nevertheless. Now, you can derive a little bit more from this as you probably know. Let's see, why am I preserving this here? Assuming that what I've just said is okay, and the codimension is bigger, and so on, then you can look at homogeneous factorizations of perm times L to the something, right? L to the C. And try to write this as the determinant of something. Determinant of A. And in that case, you can write A. Well, you only have one new variable there. That's, we think of L as a variable. So you can rewrite, if you decompose this matrix as, this is supposed to be a linear matrix again. If you decompose the matrix, just thinking of the only variable as L, then of course it would be a diagonal matrix. So it's some power of L, and you have some CLs down the diagonal. This is C of them, and then other stuff elsewhere, and maybe on the diagonal too. Right. So the matrix has to look like that, where the stars represent variables that appear in the permanent, and the L's are the new variable, and then there's some zeros up here. Maybe this is the size of the permanent. So this is perm n, this is n. Right? That's, you can always reduce to something of that kind. No, I didn't say that right. Some zeros. We don't know how many because we don't know which power of the determinant.
I think there can only be 1 0 over there.
And that's what I was about to say, is that there can only be 1 0 on that. So then A has this form. And this is the fact that you can derive from this fact.
And it's not C, some other number.
Sorry?
It's not C terms on the diagonal.
No,
We
it's
don't
not
know
C.
how.
It's something else. But I do have a term here which is L to the C. Why isn't it C?
Times 0.
Times 0. Good point. Good point. Right. Right. Thank you. So, in fact, this is an n by n matrix. And the statement is that there are n minus 1 of these on the diagonal, right? And a 0 off. So that's a consequence of this rank matrix. And Frank and I began to play around and try to use this to show that there was no 5 by 5, maybe matrix factorization of the permanent, but we didn't quite succeed, at least not yet.
Can you just say again which vector space or which R module, whatever, that A is going to live in from your description?
Sure.
Just didn't
So
catch
if
all
I
the
take
stars.
R to be this ring, then A is a map from R to the N, in this case, to R to the N.
S is the ring with the new variable L.
And S, I guess R is, yeah, that's right. L.
So n squared plus 1 variables.
All right, so there's one other exponentiality which we actually understand, and I wanted to briefly tell you what that was. And that comes from some of it is old work due to P.M. Cohn. Some of it is new work from things that Peva and I have done recently. And that's the case of quadrics. So let me show you two very special rings. This is the old result, proposition, which is that if, let's suppose we work now with S again, and now there are maybe n variables, C, n variables, x1 up to xn. I'm going to work homogeneously with polynomial. It doesn't matter very much because I know the theory there better. And I take f equal to x1 squared plus xn squared. Okay? And I ask, what are the matrix factorizations? And well, there are, you can write this as in different variables, z1, z2, plus z3, z4, plus and so on, and use Canara periodicity, and you get some matrix factorization. And since every time you add 2 squares, the rank doubles, then, for instance, if n is even, the size of the matrix factorization you get is 2 to the n minus 1. So every matrix factorization has size divisible by 2 to the n minus 1.
Maybe n minus 1 divided by 2.
Does seem to be n minus 1 divided by 2, doesn't it? Or maybe n divided by 2. Let's say n is even. Just to simplify, this is a similar result for n on n over 2. That's right.
So how does this compare with Clifford's theorem?
So let's see. Which Clifford's theorem are you thinking?
That classifies Clifford algebras.
Yes, right. So this comes from the classification of Clifford algebras. And in fact, the analysis of matrix factorizations over quadratic forms really comes down to Clifford algebras. And you might well try to do things like the permanent with more general Clifford algebras. So you could ask, in general, you have this factorization, AB, and you have T, and remember, or think of it as D of D, you had an equation D squared is equal to F, right? That was or F times A, maybe F times T. So if you think about this as if this were a variable and F were an element, then this is like a Clifford algebra equation, right? So if you have a square of something equal to F times an element, you should think of the Clifford algebra, or maybe the homogenized Clifford algebra, because of that T, is appearing. And in fact, this X that you get becomes naturally a module over the Clifford algebra. So the size of the matrix factorization is really the dimension of the irreducible module over the Clifford algebra of that quadratic form. And this is something that can be extended somewhat and leads to lots of nice things. Frank has used this, and we worked on this together too. But that's what happens here, and it's true more generally for some other cases. So let me show you another case, which is a recent theorem. Suppose you have any regular sequence of quadratic forms. This is a theorem of Tayeb and mine. Any regular sequence of quadratic forms. That just means that the variety defined by these F's in projective space is empty. Right? It's as small as it could be. The only place in which they've all vanished together is when all the variables are 0. This is over an algebraically closed field, I guess. It doesn't even need that. Quadratic forms. And suppose you, let's say, in x1, xn, over a field C. And now let's introduce n new variables and work instead over the ring C with variables z1 up to zn joined as rational functions now, with then x1 up to xn. Let's call this S prime. And look at the new quadratic form over this big field, which is summation zi xi. Sorry, zi fi. So in this case, I would put generic coefficients in front of all these x's, x squared. Right? Summation zi xi squared is an example of this. So e.g. summation vi xi squared. So I want to think of this as a single quadratic point. Then the matrix factorizations of this thing are all of size 2 to the n. That's what I wanted to say. 2 to the n minus 1. MFs all, this is the big F, have size divisible by 2 to the n minus 1. And that should be the situation for sufficiently generic polynomials in n variables of any degree. So the question is, one question is that true? Or something a little weaker maybe for the permanent. So maybe that's a good place to stop and see if anybody has questions. Yeah.
So, is there anything known about what happens if we allow in the matrix factorization non-squared matrices?
So I don't know much about that case. You can't, the usual definition of matrix factorization, which I short-circuit a little bit, is AB equals BA equals F times the identity. And then this implies that A and B are squared. But of course you could forget that.
Yeah, or we could
Then this is true in a very much more general circumstance. You can have this kind of thing very much more generally, because you can always write F as, you know, a linear combination of the variables with coefficients of lower degree. So this formula alone is rather weak, I think. But if you put in BA2, then it becomes strong. So the answer is I don't know, really. Yeah. Was there a
Well,
comment?
how about, so, you know, usually, so BA would have a different size, but you could have F times something of that.
So if you think of it, you know,
I guess I'm thinking that you have, if you look at the eigenvalues of AB and those of BA, other than zeros, are the same, or roughly.
True, but yeah, that's true. I mean, let's say n is bigger than m, right? And I try to do this. Then this cannot be multiplication by f, right? Because it has low rank.
Sure, the F times that.
But I could have
F times the
eigenvalues
projection
after and
matrix.
then zeros.
Yes.
I wouldn't be surprised if that reduces to the matrix factorization case, but I don't know. I don't know.
Yeah, why can't you just like either pad by zeros or truncate?
Well,
and
that's
just-
what he's.
An example would be pad by zeros.
Yeah.
But whether that's the only example, I don't at the moment see through. I can invert f and then the sequence is split that way, but before I invert f, I do. Yeah.
Do you have some general tools to prove lower bounds on size of matrix factorization?
I wish. So matrix, let's say,
Or at least that works for some polynomials?
quadrics. I understand quadrics. I think that people don't understand other cases very well. You know, I mean, anytime the Picard group of something is trivial, then there are no matrix factorizations where the determinant is the polynomial itself. You have to get the square. The determinant of A, right? So I didn't emphasize this, but there's this basic relation that if the determinant of A, so AB equals BA equals F, let's say we have a matrix factorization. Then the determinant of A, as we said, is a power of F, some R, Rth power of F. And R is, in a natural sense, the rank of the co-kernel of A. That's the basic relation here. Now, if there are no nice modules of rank 1, then R has to be bigger than 1. That's what I just tried to say, not as clearly as this. And there are cases in which the singular locuses of high codimension, for instance, when we know that there are no other modules of rank 1. Now, knowing that there are no modules of rank 2, it would be nice if there were Lefschetz theorems like that. Do you know any such thing, Frank?
No.
So they're somehow, you should think vector bundles here on some variety, some structured variety. And, a vector bundle should be a representation of the fundamental group in something, if it's flat or something like that. So maybe and there are Lefschetz theorems for fundamental groups, so maybe there's some things that someone will understand someday, but I don't know any such theory, unfortunately. Yeah. It's not implausible that there could be such a thing, but I don't know. So one is special somehow in our knowledge. Now, there are upper bounds known, and they're very satisfyingly exponential. People have studied, actually I don't remember what the best result is for the size of a matrix factorization. The one I remember is, which will interest you the most anyway, is the size of a matrix factorization with a linear matrix. And if you write down any polynomial and ask for a matrix factorization with a linear matrix, they exist. That's not a trivial theorem. That, in fact, comes from a Clifford algebra kind of calculation. And the best known bound is basically 2 to the number of monomials in that polynomial. Absolutely awful.
That's an upper bound.
That's an upper bound, right. I would guess that the right upper bound is 2 to the number of variables, but I have no idea how to prove that. I would love to prove it. Yeah.
Can you say a little bit about why the matrix factorizations in this last theorem need to have at least this set?
At least, you mean this?
Yeah.
Yes.
If it's possible.
So, the theorem that's behind that is that the Clifford algebra of this quadratic form is a division algebra. That's what the theorem really says. And so, as I said, these, if you look at X, there are really only 2 different X groups, right? There's X, the even X and the odd X in high degree. And they become modules, or the sum of those 2 becomes a module over the Clifford algebra. So if the Clifford algebra is a division ring, then, of course, it has dimension a multiple of 2 to the n, which is the dimension of the Clifford algebra. And so that's why this is true. So this is just a shadow of the theorem that the Clifford algebra is a division algebra. Actually equivalent.
So I think maybe we can end, and if there's any more questions, we can talk over lunch. Let's thank David again.
Bring your lunch.